This video clip develops a solution to exercise sheet 3, question 3. In this question, return to the VAR1 process of question 1, and we look at its moving average representation and also impulse response functions. To remind ourselves of where this moving average representation comes from, let's go back to the general case. Assume that yt is a VAR-P process. That means I can write it as a matrix polynomial phi of L times yt equal to white noise, using here the fact that alpha is 0, and that's given in the question. And if yt is a stationary process, then that autoregressive polynomial is invertible, so we obtain the representation that yt is phi of L inverse times epsilon t, and then we just write phi of L inverse as another polynomial theta of L times epsilon t, and that's just going to be an infinite order polynomial with terms that are going to look like theta 0 times epsilon t plus theta 1 times epsilon t minus 1 plus theta 2 times epsilon t minus 2, and so on going backwards. And actually I should have written a 2 subscript on that last theta, so the third term is theta 2 times epsilon t minus 2. Now returning to the question, we go to the VAR1 process and we're asked to calculate the theta 0, theta 1 and theta 2 associated with this process. In this case we have P is equal to 1 because it's a VAR1, K equal to 2 because it's a bivariate VAR. The easiest way to uncover those theta matrices is via back substitution. So writing out for yt using the data generation process we're given in the question. We're then going to substitute for yt minus 1 using the same equation but just lagged 1 period. And then collecting the terms together. So you're going to have phi 1 squared yt minus 2 plus phi 1 epsilon t minus 1 plus epsilon t. Again, substituting for yt minus 2 using the data generation process lagged 2 periods. We get the following expression. So, and again, collecting terms, we obtain the following. So you see that now we have an expression for yt involving yt minus 3, epsilon t minus 2, epsilon t minus 1 and epsilon t. Okay. Now if we continue doing the back substitution for yt minus 3, you can recognize that all that will introduce is terms involving epsilon t minus 3, epsilon t minus 4 and so forth going backwards. So we already have enough information to work out what the theta matrices are that we're trying to uncover, because we can compare the coefficients on the terms epsilon t minus 1 and epsilon t minus 2 from our back substitution equation that we've just derived with those from the infinite order moving average representation, and the coefficients must match. So our theta 0, the coefficient on epsilon t, that's just the identity of order 2. Theta 1, the coefficient on epsilon t minus 1, that has to be phi 1. And theta 2, the coefficient on epsilon t minus 2, that has to be phi 1 squared. So for this particular question, given the values of theta that we have, so theta 0 is just the identity of dimension 2. Theta 1, we plug in the values that were given in the question. For phi 1, it's 0.6, 0.1, minus 0.6 and 1.1. And then for theta 2, this will just be phi 1 squared, in other words phi 1 times phi 1, and if you multiply that out, you'll find the answer becomes 0.3, 0.17, minus 1.02 and 1.15. Now moving on to part B, we're asked to calculate certain impulse responses for this VAR1 system. Recall that the impulse response of a unit shock to jt on yi t plus s can be defined as the partial derivative of yi t plus s with respect to the shock to yjt, which is just epsilon jt. This partial derivative can just be read off directly from the infinite order moving average representation. And so it's going to be equal to the ijth element of the matrix theta s, something we wrote in lectures as little theta ij with a superscript. We're asked to calculate the impulse responses for s equal to 0, 1 and 2. So we can make a little table, putting the value of s across the top, and then the values for I and j down the side here. So the entries of this table are going to be the appropriate theta ij superscript s values that we calculated in the previous part. So for s is 0, I equals 1, j equals 1, then that's 1. When s is 1, it's the 1, 1 element of theta 1. S is 2, it's the 1, 1 element of theta 2. And now when we go to I equals 1 and j equals 2, again it's the appropriate element from the theta matrix. This will be 0 at s equals 1. The 1, 2 of theta 1 is 0.1, and the 1, 2 element of theta 2 is 0.17. Then with I equal 2 and j equal 1, we need the 2, 1 element of theta 0 here, which is 0, the 2, 1 element of theta 1, which is minus 0.6, and the 2, 1 element of theta 2, minus 1.02. And then finally, for s equals 0, j equals 2, I equals 2, it's going to be 1, 1.1, and 1.15. So actually in this table we've answered both parts 1 and 2 together. And so the answer to part 1 is given by the first and third rows of our table, and the answer to part 2 is given by the second and fourth rows of our table.